Okay, let's start 11.3. So, like I said, I'm going to call this 11.3 as far as the sequence of our notes is concerned. But if you look in the textbooks, if you want to reference some of the stuff in for this particular video, you're going to be looking for section 14.5. And this section is going to cover weak acids. And weak acids act quite a bit differently than strong acids do. Equilibrium constants are needed for weak acids. The equilibrium constant is going to tell us how much this weak acid dissociates. We do not need equilibrium constants for strong acids because we know that they dissociate at 100%. So if you have 6 molar hydrochloric acid and you want to know what's the concentration of hydrogen ions, you automatically know it's 6 molar because they dissociate. The hydrogen and chloride molecule dissociates completely into hydrogen ion and chloride ions. That's not the case though for weak acids. So we want to think, okay, well, how much does actually dissociate? So we use this thing called Ka, which is the equilibrium constant, K, the same K we used in the previous chapter, but the subscript A references, okay, this is an equilibrium for an acid. I've just got a general equation on the board here. We've got the hydronium ion, which is H3O+, and then the conjugate base, so the A negative. Those are going to be the things that are on top of your equilibrium expression. On the bottom of your equilibrium expression, you're going to have the concentration of the acid that you're originally working with. Again, notice that water does not show up in the equilibrium expression because it is a liquid, and it is not being produced. It is not going to actually increase in concentration. Now, weak acids typically have a Ka that is much less than 1, or at least a little bit less than 1. Again, this is very different than what a strong acid would have. If we would go ahead and want to try and calculate the Ka for a strong acid, it'd be incredibly huge because the denominator, Ha, would be essentially 0. So having a Ka that's less than 1 leads to relatively small H3O+, and relatively small A negative that are going to be in solution. And so usually with weak acids, we get a pH of about a range of 2 to 7. We saw that with the acetic acid. We had it about 3. I added a whole bunch of more acetic acid, 1 molar, and I still couldn't get it to drop below 2. Again, that's because we do achieve equilibrium at some point, and we cannot actually dissociate any more hydrogen ions. So we keep that pH range between 2 and 7. All right, so let's do some work with these. Let's say I've got 1 molar HOAC. Okay, that's going to be acetic acid. All right, HOAC. If I draw out the structure, maybe I can do this in class tomorrow. You'll see where that comes from. So we got 1 molar of this stuff. We want to calculate the equilibrium concentrations of the acetic acid, the hydronium ion, the acetate ion, and the pH at the end of the day. So our first step here is going to be to define the equilibrium concentrations in the ice table. Now we're going to do so using numbers and variables. We know the initial concentrations. We've got 1, 0, and 0. We place this material inside of the water and dissociation starts to happen. Not a lot of it, again, it's a weak acid, but some does occur. So we get a change. And it results in this. Now, one question you might be asking yourself, well, Cornick, how do we know what the change is going to be here and here? How do we know it's X, or how do we know it's 2X, or what are going to be those changes? Again, we can look at the equation, but these are all what we call monoprotic acids. So that means they have 1 hydrogen that they're willing to give up, and in this case it's that hydrogen right there. So this is our equation. We look at the back side of that. We've got the H3O+, the hydronium, and then the conjugate base over here. Okay. Oh, side note, is this a strong or a weak conjugate base? It's a strong, right? Because this, being a strong base, makes this a weak acid, and we know that it's a weak acid. Okay, so we now have an ice table that is pretty well developed. Let's move on. So we've got, again, 1 molar HOAC. Calculate the equilibrium concentrations of HOAC, hydronium, OAC, and the pH. We've got to write the Ka expression, and here it is. Now, weak acids have dissociation constants that have been defined. Let's see, I'm just checking my textbook here. To see if I can find where those defined Kas are. And it looks like I can. So I'll talk more about that tomorrow. Well, it's usually going to be given to you in the problem, it looks. I'm looking on page 641 of your text, and that's kind of the problem that we're looking at here. Calculate the percent dissociation of acetic acid when the Ka of acetic acid is 1.8 times 10 to the negative fifth. So that number, the Ka, is going to be given to you in the problem. All right, so we've set up the equilibrium expression. Notice we have x squared over 1.00 minus x on the right. And if we take a look at this closely enough, we'll see that this is a quadratic, and we'll need to solve it using the quadratic formula. I'd like you to go ahead and pause the video right now and give that a shot. It'll be good practice on your quadratic. Okay, so hopefully you did that. And now I'm going to make you mad, because I'm going to say, or you can make an approximation if x is very small. And that approximation is going to be called the 5% rule. There's actually a rule of thumb that we're going to have to follow. So this will alleviate our need to do the quadratic formula about 70% of the time, which is kind of nice. So let me show you this approximation idea. First, let's go ahead and assume that x is very small. We can usually do this. If you look at Ka, it's really small, okay? And this is a weak acid, so we should be able to think that there's not going to be a whole lot of dissociation going on. So the acetic acid is going to remain pretty much close to 1.00 when all is said and done. So this x is going to have little effect on that. But we don't know that for sure. So again, we're going to assume that x is small because Ka is so small. So if we do that, our equilibrium expression now looks like this. It's obviously much easier to solve. We'll just have to take the square root of 1.8 times 10 to the negative fifth. And if we do that, we'll find that x is 4.2 times 10 to the negative third. Okay, so there's our x value, one of the things we were looking for in the original problem, because that's going to give us the concentration of, directly, that and that. Now, the 5% rule. Now, does this work? Does our approximation hold true, or do we have to go back to the quadratic? Well, here it is. If x is less than 5% of the original HA concentration, then the approximation is okay. So we solved for x, we got 4.2 times 10 to the negative third, and the original concentration is 1.00. So if I take 0.0042 and divide it by 1 and multiply it by 100%, I get 0.42%. And that means that, since it's less than 5%, our approximation certainly is okay, and we don't have to use that quadratic formula. So then to finish the problem, they did ask us for the pH of this particular substance. So now we take the negative log of 4.2 times 10 to the negative third, and if you do so, you're going to get a pH of 2.37, and again, that falls right inside that window of weak acids. So we had a 1 molar acetic acid, and now we're coming out with about a pH of 2.37. So that's actually what I used in class today. I used 1 molar acetic acid. Now, I diluted it, didn't I? Yeah, I put it in about 340 mils of water. So that's what allowed us to have probably a higher reading of a pH with our Vernier pH probe. Okay, let's try a different one now. This will show us why sometimes we can't use approximation. Let's say we've got formic acid, and we've got a very small concentration of that formic acid. So just 1 times 10 to the negative third. Here is the equation for formic acid, and I've given you the acid dissociation constant as 1.8 times 10 to the negative fourth. Kind of made a boo-boo there. All right, so I've given you enough information. If you didn't see that last little blurb right there, I'd like you to go ahead and do this 2 ways. I want you to do it using the approximation, because that's the nicer way. And then I want you to do it using the quadratic formula. And when you're done, then play the video again. All right, go ahead and pause it. Okay, so let's come back. All right, if you made an approximation the first time, you'd come up with about a pH of 3.37. On the other hand, if you did it exactly by using the quadratic formula, you should have come up with something a bit different, and that's 3.47. This is actually quite a big difference. Okay, the pH scale is logarithmic, so it's not like this is just 0.1 times bigger, or 0.1 more, I should say. It's actually much larger than that because everything is exponential. So it is important in this case that we don't use the approximate, that we actually have to use the exact method. All right. So let's recap Ka, a couple of things. If we increase in acid strength, if we want to increase our acid strength, then the Ka has got to go up, and the H3O plus has to increase. And what has to decrease? Well, the pH has to decrease. So that's a nice relationship idea between Ka, pH, hydronium ion concentration, so on and so forth. You can probably think of a bunch of multiple choice questions that could be asked based on these principles. We'll get to bases actually tomorrow in class, but just to preempt you, if we want an increase in base strength, we'd have to increase the Kb, which then increases pH, but look what it does to hydronium concentration. It decreases that. So you can see your hydroniums kind of switch places with one another, and then you can also see that your pHs switch places with one another. All right, last thing then for today is this idea of percent association. Sometimes it's nice to know not a Ka, an equilibrium expression constant, but a percent dissociation. So what percent of this particular weak acid does actually dissociate? And we have a nice nifty equation that allows us to figure this out. It's just the percent dissociation equals the amount dissociated divided by the initial concentration times 100. So it's a pretty simple expression. For a given weak acid, the percent dissociation increases as the acid becomes more dilute. So if we add more water, dissociation is actually going to increase because there is more water to kind of separate out that weak acid. Okay, so that number is going to go up. So let's do some work with percent dissociation. We've got a solution of 8 molar formic acid. It's 0.47 ionized. 0.4% is ionized in water. I'm going to calculate the Ka value for formic acid. If we work this in reverse, we should be able to remember that Ka for the formic acid is just the CHO2 negative ion and the H3 plus ion on top divided by the material on the bottom, which is going to be HCHO2. So we are looking for Ka. We do know the concentration, the initial concentration of the formic acid, but we don't know a lot of other things. We don't know this guy, and we don't know that guy. So it's going to be pertinent to find those. Once we find H3O plus and CHO2 negative, we'd be able to use an ice table to go ahead and figure out the concentration or the value for Ka. So the question arises, how do we figure out that in that? Well, that's where this percent dissociation is going to come into play. So here's what we do. Your percent dissociation, in this case it's 0.47%, equals the amount dissociated. So amount, we'll call that dis, over the initial concentration. In this case, the numerator is the unknown. We'll call that x. Divided by the initial concentration, well, that's 8. Remember, this is a percentage, so times 100. So you'll divide 100 from both sides. You get 0.0047 equals x over 8. And then you can solve for x. When you do that, x is going to equal approximately, I think you get like 0.038 molar. That's how much dissociates. So when I said before, we need to figure out CHO2 negative and the hydronium ion We needed to figure out what their concentrations were. We now have that. That's 0.038. Okay? So you can go ahead and plug in your ice table and you can find your value. Go ahead and do that now. You can pause the video and then come on back and I'll show you what the answer is. Alright, so your end value, if you did that all correctly, is going to come out to a Ka of 1.8 times 10 to the negative fourth. Alright, that's weak acids and percent dissociation.